So hi, everyone. Welcome. I'm Nicolai, and this is going to be you, me, and we talk about why don't they just do the thing that I want them to do. They, in this case, when I first started working on this talk, were they the people at Oracle. But by now, I'm actually on the team myself, not as a developer, though, but as a Java developer advocate at Oracle. So some of this was actually checked by the people on the inside. So it's not all just made up by me. OK, so we have a couple of things to talk about. I've prepared 5 topics. If you want to go to the slides, if you want to see the slides, you can already do that now. Just go to slides.neatpathx.dev/just. I'll copy it in chat as well. So you can see the slides there if you want to. Just use the page up, page down buttons for navigation. That works best. OK, so first one. Why don't they just let us add fields to records? So this is what we want. Right? We got these new records. They're pretty cool. We can give, just say record, the name, and then you put all the things in the components in the parents. But wouldn't this be nice? Like, I just want to add an additional field without any accessors. Why can't I? That would be so easy. So why would I even want that in the first place? Well, obviously, I want to benefit from encapsulation. We've been taught that encapsulation is a good thing, so I want to use that. But also, I want to reduce my boilerplate. That's what records are there for, right? And the answer is just a plain no. No, records are about neither. They're neither about encapsulation, nor are they about reducing boilerplate. Records have a very strong semantic meaning. And that is that records are classes that act as transparent carriers for immutable data. And we're going to focus on the transparent part here. And this transparency inspires a motto for records. And the motto is, maybe you've heard that before, the API for a record models the state, the whole state, and nothing but the state. Right? So that's what records are about. And this transparency, this requirement of transparency, implies certain restrictions. Right? So you need an accessor for each component, or the API wouldn't model the whole state. Or rather, the API wouldn't model the state itself. And the accessor also has to have the same name and the suitable return type. So all of that has to reflect the component exactly. Then you need an accessible constructor, which has one parameter per component. Or otherwise, once again, the API doesn't model the state. Right? If you can't take state and turn it into a record, then there is a mismatch there. We can't have additional fields. If we had additional fields that were private and didn't have an accessor, then the API wouldn't model the whole state. And we also can't have class inheritance, because then other parts of the record, so to speak, other parts of the class could also have more state lugging around. But the important part here for us is no additional fields. That's what we're talking about, right? So this requirement for transparency is the reason why we cannot add additional fields, because if we could, then the API wouldn't model the whole state. Now, I could leave it at that and say that's the answer, but that just really pushes the thing down the line. Why is it so important that they're transparent? What's the deal with that? So records were designed to be so-called nominal tuples. So what does that mean? First, nominal. Java is what's called a nominal type system. That means types in Java have names, and they're distinguished by their names. You can have 2 types that do the exact same things, but they have different names, and so they are different. If you use TypeScript, then that is probably the most common counterexample. They have what's called a structural type system. If 2 types have the exact same structure, say you have 2 types that have a string field called name, now these 2 types are structurally identical. They may have different names, but that doesn't matter. You can interchange them. And that comes with some interesting development experience if you come from a nominal language like Java. Anyway, so that's the nominal part, and that's not even the important part for us. The important part for us are tuples, which is a mathematical concept. Pairs are tuples, triples are tuples. And for a type to be considered a tuple, it must conform to these restrictions. And I have a link in here to a long blog post that I wrote that explains this in a bit more detail on the math. So these restrictions come from transparency, and this transparency comes from records wanting to be tuples. Yet again, that just pushes down the road. Like, why do they want to be tuples, though? And this is where it becomes interesting. If you have a tuple, if your type is nothing more than a combination of values that you can put apart and also put together and also take apart, if you can do that easily and losslessly, that's when you can start doing a few cool things with this. And that's the reason. Records are tuples which require this transparency, because then you can do a few things. And I've got 3 things here that I want to show you. The first one is destructuring. You know what, Brian, since you typing that, I think, did I understand this correctly? Can I force people to use a certain layout? I think I can, right? Apply layout.
You cannot. I can try, but this is the best layout, and they have the ability to do that to do it themselves. So
yeah, I think I cannot force people to full screen. So anyway, I'll go on. Right, so destructuring, that's one of the cool things you can do. So in JET 405 proposes record patterns. So they're still down the line. They're still not in Java yet, but they hopefully will be at some future point. They likely will be, since there's already a JEP. And what you can already do nowadays is this, right? Range instance of this other thing. That's a regular instance of check. And since Java 16, we finalized type patterns. So you could just assign range to a variable. And what destructuring means, or deconstructing means, is that you will be able to take these instances apart into their component parts. So let's say I have a range that is a record that has a low and a high value. And this check, what it does is it says, OK, is the thing that I get actually a range? If yes, then take it apart into its components low and high. And then I continue with the checks. Also, if high is smaller than low, which is weird, right? Should be the other way around. So I'm going to return a new range that's then has high and low switched around. So this basically what this means is if my range is broken, let's switch around low and high so that's the proper range again. The important part about this is I took the range, the original one, apart here, right? This range, I took it apart into low and high, and then I put that back together. And I know, because of transparency, that there was no hidden state here that I lost. The original range could not have any further state that the new range now doesn't have. That's an important part here. That's how I can reliably use this feature in a safe manner. I can even reconstruct the instances that have the same values for whatever reason, and I can be 100% sure that nothing changed. There's no hidden state that I could have lost. Then there is something like this that we might get in the future. Nobody knows yet, right? So this is not this is going to happen. This is maybe this could happen. And what could happen here is, let's say, once again, I have a range to begin with. And then maybe I want to have another range, which is like this one, but the low value is different, right? So I want to have the same range, but with a different low value. And there might be a future Java version which allows something like this. The syntax is made up, right? But it could look like this, where you say, OK, take the original range. Then I take a new keyword called with. So I take this. Basically, I say, OK, take this range apart. Then I reset all the values that I want to change. And then once that is done, recreate a new range instance. So I have the original range, 5 to 10, which is unchanged by this. And now I've got a new range from 0 to 10, which is the new one. So the 10 was transported from this range to this range. And once again, this would only be possible without losing hidden state if we follow these strict rules of transparency. And the last one I got for you is serialization. Oh, wait, what's that there? That doesn't belong there. We can just fix the slides live. There you go. So transparency also makes it easier for records to be serialized and deserialized. You should easily see that, right? Like if you want to take an object apart and store it in its individual values in a serialized form, it's much easier if you can easily get at those values, as opposed if you have to use deep reflection and try to get to fields, and then when you put them back together, maybe there isn't a constructor that accepts all the fields, so you have to create an empty object bypassing the constructor and all the safety that it allows, and then set individual values. All of that is what reflection does nowadays, and serialization does nowadays. And if you're serializing, there you go. And if you're serializing a record, that means that the code that does that is easier to implement and maintain, but also our code that uses this is easier to write and maintain. It's safer and it's faster, and there's an entire Inside Java podcast episode that I want to recommend that goes into this, why this is better for serialization. So to summarize this part, records want to be nominal tuples, and that requires transparency, And that requires that we don't have any additional fields, but in exchange for transparency, we get additional features like safe destructuring with blocks, better serialization, things that wouldn't be that easy or that straightforward without these restrictions. But on a higher level, so this was the summary specifically for records not having fields. Taking either one step back or going one level higher, whatever. In this case, it might make sense, not always, but it can make sense to introduce something that has restrictions if those restrictions enable other features, right? So there's sometimes a trade-off there between how much freedom do we have as developers versus how powerful can the language be, because it can make much stronger assumptions based on these restrictions. If you have any questions about any of this, just ask ahead. Other than that, I'll just keep going. So why don't they just let streams handle checked exceptions? Oh my, that's the good one. That is so annoying. I still remember when starting with Java streams, I was all hyped, and then I ran into the first exception throwing methods, and then it got all complicated, and then I was frustrated, and at some point I actually sat down and tried to create an API that does that. And it's not as easy as it might look. So this is what we want, right? Let's say we have two methods. One of them is called compute, takes a string, returns an int, but that does not matter at all. The thing that matters here is this. Compute throws an IO exception. Similar to supercharge, nobody knows what it does, but it can throw an interrupted exception. So these are important parts. Compute throws IO exception, which is, of course, checked. Supercharge throws an interrupted exception, which is, of course, checked. And so ideally, we could do something like this, right? So we got a stream of foo and bar, we compute, then we supercharge, we turn all of this into a list. And because these two methods can throw, or rather these two methods can throw, we would like to be able to write a try-catch block around that catches these exceptions. And then also write, and then this should not be a compile error, which it would be nowadays. So that's what we want. Straightforward, simple. Why didn't they just do that? Okay, let's think this through. To make this work, we need an exception-throwing function interface. And we need to make changes to the stream methods so they also throw exceptions, right? And the first attempt could look like this. We have a new function interface, which has the common apply method, but this one allows to throw an exception. Well, we're passing this to map, so it would be kind of interesting. It would be straightforward, just have map throw that exception, right? So we have a stream here. We give it a function that maps from E to out, so we return a stream of out. But map can throw an exception because the function can throw an exception. Well, that's not correct though, because streams are lazy. Map never applies the function. Map only stores, well, this is the stream step before me, and this is the function we want to apply, and then let's do nothing until the terminal operation is the one that triggers execution of the stream pipeline. So this entire attempt is totally incorrect because it's a terminal operation that has to declare the throws. Okay, so then we could just do this, right? Just keep the function interface as it was before, just like the common apply, but it throws an exception. And from the stream interface, we move the throws from map to toList, which in this case is the only terminal operation, which is probably not the only one you want to have in reality, but for now that's enough. Now this is not going to help a whole lot. It's correct, right? You can now write something like this, but you have to catch an exception. But which one? This is supposed to be IO. This is supposed to be interrupted. I have no indication of that. I just can catch exception. That's all. I mean, of course, I could catch IO exception, but I have to know that that's the one that I want to catch here. So that's not great. But even worse, let's say I start with my foo and bar, and then I just map the word to word. I do nothing, and then I call toList. Still, I have to handle the exception, right? Because toList now throws. So it throws every time, or threatens to throw every time I use it. That's horrible. So, OK. So the compiler doesn't know the exception type, which is a problem. And we have to catch the exception every time. So the better way would be we need to somehow have more specific type information than just exception, right? That's what we need. So let's try to capture the exception in a generic parameter. Okay, that's the first step we could do. Okay, let's say the function, it has in and out as before, but now we create an additional third type variable, which we call x, like exception. And then we say the function throws that one. And then the stream now also not only has the element type carrying around with it, it also has the exception that it carries around with it. So say you have a stream and you call map, and that function throws the function exception. That's what this FEX means, right? Then we return a stream that throws the function exception, right? So we change the parametric variable of the stream when we map. So the element changes, of course, the element type, but also the exception type changes. And in the end, the toList just throws this exception type. Well, we're getting closer, but it doesn't do the trick yet. So when we call compute, we get a stream of integer IO exception, because compute can throw an IO exception. But when we supercharge, then we go from IO exception to interrupted exception. Like the way we wrote it, we lost, or I wrote it rather, we lost the old exception type. So I can catch, the compiler wants me to catch an interrupted exception. That's great. That's exactly what we want. But nobody tells me that I have to catch an IO exception. And if I try, it doesn't even work because it's not declared. So it's a compile error. So that's not good either. Damn it. So what do we do? So only the last function's exception type is called, and not the other ones can't. So that's not ideal. So we need to capture all exception types. That's a challenging part here. Okay, so attempt number 4 is we try to merge the exceptions in the generic parameter. Okay, now this is a complicated method to read. I understand that. So first of all, it's a static method because it only works as a static method. Its input, it takes a stream which throws some kind of exception, and it takes the mapping function that throws another kind of exception. And now this is where the trick comes in. We define a new variable, a new exception variable, type variable. Sorry, these are all type parameters, right? So in and out, that's as we used to. But we declare an a new exception type that can be any kind of exception, but the stream exception has to extend it, and the function exception has to extend it. So that means we have the streams exception here. Now the function comes on top. We have the function exception, not on top, but extra, right? We have both of these. So the stream can throw this one already. The function now threatens to throw this one. And what we're looking for is a super type for both. That's what we're looking for. And that's what this is doing. We declare a new variable for exception that the other two have to extend. And this only works as a static method, which is not ideal on its own, because we have to apply them in a roundabout way. So that's really weird. We start with a stream of this, which is a stream of runtime exception, right? And then we throws a file not found exception, so we get a file not found exception. And then this one throws a zip exception. And hey, actually, zip exception and file not found exception have the current supertype IO exception, so we can now catch IO exception. Well, that actually kind of works, doesn't it? Well, kind of, for a while. If we apply the same thing to the problem we had before with compute and supercharge, we immediately run into a situation that compute is an IO exception, supercharge is an interrupted exception, and the only type they have in common is an exception. So that's not great either. So first of all, the common case now has to lug around an exception type, which would be runtime exception. So you always have this thing here, which is horrible. Map as a static method sucks. And then we quickly have to catch exceptions anyway, because they generalize to exceptions so quickly. So we somehow need to find a way to keep the exception types distinct. I will read the chat on this later in a second, by the way, because that's an interesting topic. I already saw a good recommendation in there, so I'm going to come back to that in a second. OK, so what else can we do? Well, we can create multiple stream interfaces that differ by the number of exceptions. So we start with a normal stream interface, right? Just the element type, no exceptions here, nothing to be seen. toList doesn't throw, everything is fine. And then we pass a function that can throw an exception. And then what we return is a stream x1 that has the output type of the function, of course, right? But now it has as a parametric type the exception type of the function. And now if we look at stream x1, which has one parametric type from the exception, then toList can throw that exception, obviously, because that's a terminal operation. But if you map with the function that throws yet another exception type, then return a stream x2, which has 2 exception types. Okay, so we have that interface as well. So now we have stream x2, which can throw 2 exceptions. Probably stream to x would probably sound better, which throws 2 exception types. And if you map, so toList throws both of them, or threatens to throw both of them. But what about map? If you map again with the new function exception type, where do we go from here? Will it be stream x3 all the way up to 10? Or I just gave up. I went to stream xn. That just means I'm just going to throw exception. So after too many steps, you just run out of interfaces. So if you now use that, and you start with the stream of integer. Well, this is not a stream of integer, right? That's a stream of string. Let me see whether I can quickly fix that. Just so we get this correct. Okay, there we are. So stream of string, great. I start with that. This is a stream of string. And then I call compute, and then I get a stream x1 integer IO exception. And then I say supercharge, and I get a stream x2 integer IO exception, interrupted exception. And then toList will throw both of these, and then I can catch both of these. So it actually works. That's correct and usable, which is the first for all of these attempts. So that's good. But imagine how many additional interfaces that leads. So we have stream, and then 1 exception, 2 exceptions, 3 exceptions, I don't know how many. But we also have these primitive specializations already, in stream, long stream, double stream. So now we have all of these combinations. Ouch. That's called a combinatorial explosion, and that's not good. It's when you have to combine different orthogonal requirements, and all combinations are valid. But it even becomes a bit worse, when you actually sit down to do it. Then you realize that a function can also, of course, declare more than 1 exception to throw. Right? Some functions can throw 2 exceptions. They have 2 text exceptions. So maybe I need an overload that gets me from stream to stream x2 if I get a function that has 2. Oh my God! So it gets even worse. And to solve this, what we need is variadic generics. So this is attempt number 6. We put all exceptions into one type parameter. We just have a var_args exception, var_args generic type parameter here, and so those can be many different types. And the stream then also carries many different types with it. And map just returns the old exceptions, and then it ORs the next exception that goes in there. If you're thinking this is a bit weird, stick with me for a second. And if you do that, this would actually work. You can do IO exception, and then you basically, this operation puts IO exception into that var_arg parametric type, and then this one puts the next one in there, and then we can catch those two, and that's great. Just one interface catching all the exceptions. That's perfect. It's just one downside. Java doesn't do that. So that's not ideal, I guess. So neither function nor stream compiles, of course. So the proper solution, the good solution to streams plus checked exceptions, that's the one that doesn't work. Another solution, and now I want to turn to the chat because you said, well, perhaps we should just stop using checked exceptions, is what Pim wrote earlier. Yeah, kind of. That's one way to handle this, is to just try to get out of checked exceptions. I still personally haven't decided on whether I agree to the whole we shouldn't have started with checked exceptions. I just didn't come to a decision or opinion on that one yet. But yeah, if your code doesn't throw checked exceptions, that's one way to deal with this. I also saw the idea to just wrap in runtime exceptions. And I would not do that, because if your code does indeed typically use checked exceptions, then suddenly turning this quietly into runtime exceptions, that's not ideal. And that will lead to surprises for the people who use your code, right? They call a method of yours, and they think, doesn't this do something with the file system? Well, it doesn't throw IO exception. I think I'm good, because they have the expectation that if you would do something with file operations, then it would throw an IO exception. So that's not great. I wouldn't recommend that, actually. But I wrote what you can do is you can have something like a try or like an either and encode error cases in return values. I wrote a blog post on that I linked here, so I invite you to look into that. So the summary for this one is that Stream's laziness splits the entire exception handling into two different steps. So we pass a throwing function to an intermediate operation, but we need the terminal operation is the one that needs to handle the exception. And that's not ideal. There you go. So to be able to use a classic try-catch, we need generics to capture the exception type forward, but there just is no good solution in today's Java. But there are acceptable alternatives, right? Like with try and either, for example. So there are alternatives already. And so once again, I want to take a step back and look at this from a higher level. I don't think it makes sense to introduce something that has serious shortcomings. So none of the solutions that we presented are good solutions. They're all just like, OK, like if we have to. But they all prevent a better solution down the road, right? Because they would just be straight up either incompatible or would just lead to dead code. So that's not great either. And it's particularly bad if you already have a solution that is OK, that is acceptable, that does not bake a non-perfect or non-optimal solution into the entire JDK. So just because something isn't perfect, it doesn't mean that just every partial fix that is out there should immediately be implemented. Some problems are better left to either be fixed in user code in domain-specific ways, because the general solution is just uglier, or to wait for a proper solution down the road. And I presented the proper solution to be variadic type parameters. I have no idea whether that is possible or on the roadmap. So I'm not trying to sell you on, well, this is going to be solved soon. Just, maybe it will be, and it would be kind of sad if we had a really not good solution in place then already. OK, let's do the immutable collections, and then we'll take some questions at the end, because these are way shorter than the other ones. So what we want is immutable collections. I want to have an interface that doesn't have mutating methods, and I have a guarantee that nobody else will mutate that, which is different from unmodifiable collections nowadays, which have interfaces without mutating methods, maybe, or that mutating methods just throw exceptions. So what I really want is, we're going to use lists here. I want to assume we had an immutable list. Let's just assume that we had a class, immutable, an interface, immutable list that is exactly like list today, but it doesn't do any mutation. It forbids or just straight out doesn't do mutation. Okay, so we have list, we have immutable list. How do we put the two together? Let's start with immutable list as the super type to list. That's pretty good, right? On the left-hand side here, you see immutable list has its empty and size and those kind of methods. And then list, on top of that, adds all the mutating methods, like add, clear, remove. That's pretty good. But the bad part is also really bad. So let's have a list of agents here that we create as a mutable list. And then let's assign that to an immutable list. Well, that works because list extends immutable list. So now I can pass around an immutable list that I call section 4, and everybody will be like, ha, 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 nothing can ever change. I print section 4 for each, and nothing will happen because there are no elements in there. Great. And now somebody adds something to the original list that section 4 is just referencing. Now I go back to my immutable list, print again, and I get multiple. What the hell? How did that happen? It's supposed to be mutable. So that's a really bad idea. That doesn't work. So let's try the other way. List is the superclass to immutable list. Well, then immutable list isn't extended. So that means that nobody can sneak in during mutation afterwards. So this is actually mutable. So that's good. But of course, all the mutating methods are still declared. So immutable list has all of these mutating methods, presumably that throw exceptions then. But the immutable list can still be passed around as a list. So it's kind of reasonable to assume that mutation is allowed, right? Like if I get a list, I know that the contract says I cannot rely on this being immutable, but it's just the norm in Java nowadays. So I would probably have to deal with a lot of runtime exceptions. And so this doesn't really work well when you start passing these immutable lists around, unless, and that's what I do, you just say, OK, let's just try to keep mutability to a minimum in the first place. So I think that works a bit better, but it's still not ideal. So across API boundaries, it's tough to pass an instance of a type that has methods that then throw exceptions, and not just a few of them, but a lot. And the problem that we had here is that we saw immutability as an absence of something. We thought, well, immutability just means take a list, remove all the mutating methods, and you're done. But that's not true. That just gives you what I want to call an unmodifiable list here, or you can call it a read-only list, maybe. An unmodifiable list or read-only list offers no mutating methods, but it doesn't make any mutability guarantees. It just says, like, look, I don't have these methods, but I have no idea what's happening. Like, you could either make it mutable, have a type that extends unmodifiable list and does all the mutation methods, or we get an immutable list, which adds the guarantees that there will not be mutability. So we should not think of immutability as an absence of mutation. It's a guarantee that there won't be mutation. So it's a feature. It's like thread safety. Thread safety is not something you can do. It's a guarantee that something bad won't happen. But I'm pretty sure you spent some time to make some code thread safe, right? So apparently, like, it's a thing worth working for. It's a feature, but it's a safety feature. It's the absence of a problem. And the problem is that these features are inherited. Mutability, immutability, you inherit that from your supertypes. So if list extends immutable list or the other way around, one of the types ends up with both mutability and immutability in one class. And that's why it always blew up. That's why we could make none of these really work well. So the proper solution is to not make list extend immutable list or the other way around, but have this unmodifiable list as a common supertype for both. So now we need to add two new types. So let's see how this works in practice. So let's say this would be our secret service interface. There are a couple of methods that we want to do here. We want to pay agents, and since we're paying agents, we don't care about mutability. Just give us a list of agents. We don't need to modify it, right? So maybe read-only list is also a clearer name, maybe. We don't need to modify it, but somebody else can. We don't mind. We just want to pay all the people that are in there. As soon as you send all of these people on a mission, though, you don't want to change the team. But during downtime, mutability is perfectly expected, right? Because you can put new people on the team and kick all other people out. And then likewise, here we have three methods that return the three different kinds of lists. So that's what this would look like in practice, right? When we have all of these types. Now the problem is we don't live in a world where no Java code exists. Fortunately, we do live in a world where a lot of Java code exists. So this code is probably already out there, and it looks like this. It just takes a bunch of lists. Not all of them have to. Some of them could return a stream or accept a collection or even iterable, but it's not the most common thing. So in all likelihood, it would probably look like this, just dealing with a bunch of lists. So if we want to actually use these new types, we kind of have to use them, though, right? So we want to replace some lists with immutable lists, but that's source incompatible. You need to rewrite the code for that. Some of the return types want to change from list to unmodifiable list, but that's also compile time error because unmodifiable list is more general. So this would require you to rewrite code. If you want to change a parameter type from list to unmodifiable list, so meaning to make the parameter more accepting, then you would usually think that's fine, that just works, but it only works if you recompile the code against it. If you don't, you actually have to make a recompilation as well. So what that means is introducing these new types requires recompilation, rewriting code, and recompiling code. And now imagine doing this for the JDK, for all the libraries, for all the frameworks, for all our code, for the entire ecosystem. We need to migrate to this. There are other ways to do this. I'll just skip past this, but it's also a huge task that takes forever. So what I'm trying to sum up here is probably the last one. Rewriting, recompiling code across the Java entire ecosystem is probably not a realistic step to take. And from a high-level summary, if you have these changes, if you have something that's nice to have, that doesn't cut it on its own. You also need to explain how it's maybe not nice to get, but at least, at least achievable. Just nice to have isn't enough if it splits the ecosystem into old and new and takes forever to fix for a benefit that I personally would love to use, but can also probably be described as incremental. And just the last summary thing, I just want to leave this here while Brian asks me questions, because I think I ran totally out of time. Thank you.
But to be honest, it was great hearing this, Nicolai. We have 2.5 minutes left of questions, so I would just be quite quick. You already said something about getting rid of checked exceptions. Well, somebody's commenting on that, like Kotlin and Scala did. You pretty much already answered that question. That could be, but it depends, right?
So I said that I personally didn't come up with an opinion yet on whether I think that would even be a good thing to not have checked exceptions. I'm pretty sure that the Java development team also, I'm not sure what their position on this is actually, but once again, it's the difference between, well, even if that would be the better world, are we now willing to basically entirely cull this feature and just cut it out of the language? I don't, because that would change a lot of things in how Java works, and Java engineers and developers, how we think about the code. So I don't see that realistically as a change.
No, and I had the pleasure of interviewing James Goslin once. I asked him this question: why checked exceptions? And it was just to make you think of your code. That was his basic answer, which I still love, pretty much. Nick is commenting: you could also use reactive programming because there's separate pipes for errors, which is quite a good remark. Let me check what is there.
I think the last one, my PIM is good. You also want to read the inheritance relationship as is-a. So one extending the other would be impossible. Exactly. Like then you want, right? If mutable list extends immutable list, you have to read it as mutable list is a immutable list. That sounds wrong, and the other way around sounds just as wrong. So if you spell it out like that, you're basically saying a thing that doesn't make sense.
Absolutely. If you would like immutable lists, you can also look at other collection frameworks like the Eclipse collection frameworks. They have a different set of APIs for that, but you cannot easily create a list from a list go to an immutable list and the other way around. So basically, that's the problem you answered at the end already. But we're basically out of time for now. If you have questions, I'm sure that you can ping Nicolai any moment on Twitter or mail him or whatever, because he's very passionate about it. Any last words from your side, Nicolai?
Yes, go to HTTPS if you want to get in touch, nipafx.dev, and there will be contact there somewhere. But yes, nipafx on Twitter, and I'm also on YouTube and on Twitch, and just find me wherever you hang out. I'm sure I'll be there. Thank you very much for your attention.
Hey, great for having you. Thanks for being here. For everyone who was on the stream, amazing. Go back to the lobby stream because Bert-Jan will probably be there, and we have a network carousel where you can actually meet people and interact with other people who are virtual, which is quite a nice thing in a virtual conference. So
can I do that too?
Yeah, absolutely. If you go back to whenever we're done, leave, and then you're in that. I think it's part of the program. It's called Network Carousel or something like that. So you can jump in and you will get randomly connected to somebody who is also in that carousel. So that's an amazing thing. Next talk in this track will be. Let me check in my schedule for a second.
I think Aurelia is saying that the next talk is the carousel.
Oh, the next talk is the carousel, but it's not actually this. Yeah. In this track, but don't stay in this room because all these talks have separate rooms virtually, if you know what I mean. The next actual talk will be at local time 16:45. Will be by Daniel Bryant on logging, so that will be interesting as well. And I hope to see you there as well. So, but for now, stay on. Go back to the lobby stream or go to the network carousel. Nicolai, thank you, and see y'all later.
Thank you also, by the way, for organizing this.
Absolutely, no worries. Happy to do so. See you. Bye-bye.